Good day everyone, my name is Karen Centena and I will be discussing the Chapter 2 Electronic Devices 9th edition by Floyd. Half-wave rectifier. The diode conducts during the positive half cycle and it does not conduct during the negative half cycle. So in the figure, it illustrates the process called half-wave rectification. So a diode is connected to an AC source and to a load resistor RL, forming a half-wave rectifier. So keep in mind that all ground symbols represent the same point electrically. So let's examine what happens during one cycle of the input voltage using the ideal model for the diode. So when the sinusoidal input voltage or yung Vn goes positive, the diode is forward biased and conducts current through the load resistor as shown sa first illustration. So the current produces an output voltage across the load RL which has the same shape as the positive half cycle of the input voltage. So during the positive alternation of 60 Hz input voltage, the output voltage looks like the positive half of the input voltage. So the current path is through the ground back to the source. So during the negative alternation naman of the input voltage, the current is zero, so the output voltage is also zero. So what is the output if the diode is reversed? So when the input voltage goes negative during the second half of its cycle, the diode is reverse biased. So there is no current, so the voltage across the load resistor is 0V, as shown in the figure. So the net result is that only the positive half cycles of the AC input voltage appear across the load. So since the output does not change polarity, it is a pulsating DC voltage with a frequency of 60 Hz. So the peak inverse voltage or PIV is equal to the peak input voltage and is the maximum voltage across the diode when it is not conducting. So notice that the PIV can be found by applying the Kirchhoff voltage law. The load voltage is 0V, so the input voltage is across the diode at T sub P. So ang peak inverse voltage or yung PIV equals the peak value of the input voltage or yung VPN. And the diode must be capable of withstanding this amount of repetitive reverse voltage. So for the diode in the given illustration, so sa illustration, ang maximum value of reverse voltage designated as the PIV occurs at the peak of each negative alternation of the input voltage kung ang diode is reverse biased. So a diode should be rated at least 20% higher than the PIV. So therefore, sa given na illustration, the PIV occurs at the peak of each half cycle of the input voltage. So when the diode is reverse biased. So in the circuit, the PIV occurs at the peak of each negative half cycle. So a center tap transformer is used with two diodes that conduct on alternating half cycles. So during the positive half cycle, the upper diode is forward biased and the lower diode is reverse biased. And during naman sa negative half cycle, the lower diode is forward biased and the upper diode naman is reverse biased. So, ang center tap rectifier is a type of full wave rectifier that uses two diodes connected to the secondary of a center tap transformer. So, yung input ng voltage is coupled through the transformer to the center tap secondary. At ang half of the total secondary voltage naman appears between the center tap and each end of the secondary winding. So, dito sa illustration, for a positive half cycle of the input voltage, the polarities of the secondary voltages are shown sa first illustration. So, this condition, forward biases diode 1 and reverse biases diode 2, the current path is through D1 and the load resistor RL as indicated. At para sa negative half cycle of the input voltage, The voltage polarities on the secondary are shown in the second illustration. So, this condition, reverse biases D1 and forward biases D2. The current path is through D2 and RL, as indicated, because the output current during both the positive and negative portions of the input cycle is in the same direction through the load. So the output voltage developed across the load resistor is a full wave rectified DC voltage as shown. So the PIV can shown by applying KVL around the green lobe shown for the reverse bias diode. So notice that 1/2 of the peak secondary voltage will be across the reverse bias diode. So the bridge full wave rectifier uses 4 diodes connected across the entire secondary as shown. So sa first illustration, ito yung conduction path for the positive half cycle. At sa second illustration naman, ito yung conduction path for the negative half cycle. So, ideally, what is the PIV equal to or yung peak inverse voltage? So, peak inverse voltage is equal to the voltage output. So, sinasabi dito na ang bridge rectifier uses 4 diodes connected as shown in the figure. So, when the input cycle is positive, as you can see sa first illustration, diodes D1 and D2 are forward biased and conduct current in the direction shown. So, a voltage is developed across RL that looks like the positive half of the input cycle. So, during this time, diodes D3 and D4 are reverse biased. So, sa given illustration, kagaya ng sinabi ko kanina, na during the positive half cycle of the input, D1 and D2 are forward biased and conduct current. Ang D3 at D4 are reverse biased. At during sa negative half cycle of the input, ang D3 at D4 are forward biased and conduct current. D1 and D2 are reverse biased. For example, determine the peak output voltage and current in the 3.3 kilo ohms load resistor if ang volt second is equal to 24 VRMS. So use the practical diode model. So, sa given, meron tayong 3.3 kilo ohms at 24 VRMS. At gagamitin natin ang practical diode model para sa example na ito at hahanapin din natin yung peak output voltage at yung output ng current. So, first is, hahanapin natin yung peak output voltage na which is meron tayong V sub P second is equal to 1.41 VRMS is equal to 33.9 V. Bakit siya naging 33.9 V? Dahil gimultiply natin ang 1.41 VRMS sa given na volt second na 24 VRMS. Then gagamitin natin itong value na ito para hanapin ang peak output voltage. So, may equation tayo na V sub P out is equal to V sub P seconds minus 1.4 V. So, isubstitute natin yung value na 33.9 minus sa 1.4 V. So, we can get the answer na 32.5 voltage. So, 2 diodes are always in series with the load resistor. So, during both the positive and negative half cycle, if these diodes drop, are taken into account, so yung output voltage natin is magiging V sub P out is equal to V sub P seconds minus 1.4 V. Dito natin kinuha yung equation natin para sa peak voltage. So, back to the problem, hinahanap din natin yung current. So, gagamitin natin yung formula ng current which is current is equal to voltage over resistance. So, we will divide the value for voltage which is 32.5 into the resistance sa given na 3.3 kilo ohms. So, applying the Ohm's law, we can get the output current is equal to 9.8 milliampere. So, filtering is the process of smoothing the ripple from the rectifier. So, in most power supply applications, the standard 60 Hz AC power line voltage must be converted to an approximately constant DC voltage. So, the 60 Hz pulsating DC output of a half-wave rectifier or the 120 Hz pulsating output of a full-wave rectifier must be filtered to reduce the large voltage variation. So, in the given figure, it illustrates the filtering concept showing a nearly smooth DC output voltage from the filter. So, the small amount of fluctuation in the filter output voltage is tinatawag na ripple. So, the capacitor input filter is widely used. So, a half-wave rectifier and capacitor input filter are shown in the figure. So, ang filter is simply a capacitor connected from the rectifier output to the ground. So, ang RL naman, it represents the equivalent resistance of a load. So, gagamitin natin ang half-wave rectifier to illustrate the basic principle and then to expand the concept to full-wave rectification. So, question, how is the ripple affected by the RC time constant? So, a longer time constant will have less ripple for the same input voltage and frequency. Power supply regulators. A voltage regulator can furnish nearly constant output with excellent ripple rejection. 3-terminal regulators require only external capacitors to complete the regulation portion of the circuit. So, a voltage regulator is connected to the output of a filtered rectifier and maintains a constant output voltage or current despite changes in the input, the load current, or the temperature. So, the capacitor input filter reduces the input ripple to the regulator to an acceptable level. So, the combination of a large capacitor and a voltage regulator helps produce an excellent power supply. So, most regulators are integrated circuits and have 3 terminals, an input terminal, an output terminal, and a reference or address terminal. So, the input to the regulator is first filtered with a capacitor to reduce the ripple to less than 10%. So, the regulator reduces the ripple to a negligible amount. So, in addition, most regulators have an internal voltage reference, short circuit protection, and thermal shutdown circuitry. So, they are available in a variety of voltages, including the positive and negative outputs, and can be designed for a variable output with a minimum of external components. So, typically, ang voltage regulators can furnish a constant output of 1 or more amps of current with high ripple rejection. Regulation performance is specified in 2 ways. Line regulation specifies how much the DC output changes for a given change in regulator's input voltage. The text formula is based on a DC input voltage change to the regulator due to a change in the AC line voltage. So, sinasabi dito na yung line regulation is defined as a ratio of a change sa output voltage for a corresponding change naman sa input voltage expressed as a percentage. So, halimbawa, assume the DC input to a regulator changes by 1.0 volts due to a change in the AC line voltage if the output changes by 1.5 millivolts due to a change. What is the line regulation? So first, gagamitin natin yung formula ng line regulation which is equal to delta ng output voltage or yung change ng output voltage divided by delta ng input voltage multiplied by 100%. So, gagamitin natin yung given na value to solve for the problem. May given tayo na value ng input which is 1.0 volts at may output naman tayo na 1.5 millivolts. So, we will substitute that value to our equation. Upon substituting, we can get the value of line regulation is equal to 0.15%. Load regulation specifies how much change occurs in the output voltage for a given range of load current values. So usually, from no load to full load. So yung formula ng load regulation is equal to V sub NL minus V sub FL divided by V sub FL then multiplied by 100%. Where yung VNL is the output voltage with no load at yung VFL naman is the output voltage with full or maximum load. So question, assume the DC output of a regulator changes from 5 volts to 4.96 volts when the output is varies from no load to full load. So what is the load regulation? So sa solution, we will use the formula for load regulation, which is equal to V sub NL minus V sub FL divided by V sub FL then multiplied by 100%. So sa given na problem, meron tayong value ng output na no load na 5 volts at full load naman na 4.96 volts. So we will substitute this value to the formula of load regulation so that we can get the value of 0.8%. A diode limiter is a circuit that limits or clips either the positive or negative part of the input voltage. A bias limiter is one that has a bias voltage in series with the diode so that a specific voltage level can be selected for limiting. A positive limiter is shown. RL is normally R1 to avoid loading effects. The output will be clipped when the input voltage overcomes the bias voltage and the forward voltage of the diode. So, as the voltage goes positive, ang diode becomes forward biased and it conducts current. So, in limiting the positive alternation, the diode is forward biased during the positive alternation or above 0.7 volts and reverse bias naman during the negative alternation. So, for limiting naman of the negative alternation, the diode is forward biased during the negative alternation. So, below siya ng negative 0.7 volts and reverse bias during sa positive alternation. So, example, what is the output of positive limiter shown? So the diode is forward biased when the output tries to go above the positive 3 voltage. This causes the output to be limited to voltages less than the positive 3 voltage. As a check, you can simulate the circuit with multisim. The scope shows the input and output voltage for the positive limiter circuit. Example 2. What happens in the previous circuit if the diode is reversed? So, the diode is forward biased when the output tries to go below the positive 1.6 voltage. This causes the output to be limited to voltages greater than the positive 1.6 voltage. Diode clumping circuits. So, a clumper or DC restorer is a circuit that adds a DC level to an AC signal. So, a capacitor is in series with a load. A positive clumper is shown. And the capacitor is charged to a voltage that is one diode drop less than the peak voltage of the signal. So, ang net effect of the clumping action is that the capacitor retains a charge approximately equal sa peak value of the input less the diode drop. So, the capacitor voltage acts essentially as a battery in series with the input voltage. So, ang DC voltage of the capacitor adds to the input voltage by superposition as shown in the illustration. So, question, what happens if the diode and capacitor are reversed? So, it is reversing the diode and capacitor forms a negative clumper. Voltage multipliers. Voltage multipliers use clumping action to increase peak rectified voltages. The full wave voltage doubler works by charging a capacitor to the positive peak voltage on one cycle of the sine wave and a second capacitor on the negative peak voltage. The output is ideally doubled by taking it across both capacitors in series. The illustration shown below is a full wave doubler. So when the secondary voltage is positive, ang D1 is forward biased and C1 charges to approximately Vp as shown sa may left side na illustration. And during naman sa negative half cycle, ang D2 is forward biased and C2 charges to approximately Vp as shown sa my right side na illustration. So the output voltage to VP is taken across two capacitors in series. Diode datasheet. Diode datasheets include the maximum ratings for current, voltage, and temperature, as well as other electrical parameters. Some voltage and current specifications are abbreviated as follows. The first is VRRM, the maximum peak reverse voltage that can be applied repetitively across the diode. This is the same as the PIV rating. Next is VR, the maximum reverse DC voltage that can be applied across the diode. And VRSM, the maximum peak value of non-repetitive reverse voltage that can be applied across the diode. And IO, the maximum value of a 60 Hz rectified current. And IFSM, the maximum value of a non-repetitive one-cycle forward surge current. Troubleshooting. Analysis. Identify the symptoms of a faulted circuit and eliminate as many causes as possible. Analysis also includes finding out as much as possible about how the failure occurred. Next is planning. Decide on logical steps to narrow the possible causes. Frequently, you will start with visual checks, looking for obvious defects before proceeding to measuring specific points. And lastly is measurement. Having thought about possible causes, you are ready to make measurements such as voltage and resistance readings. These results will usually isolate the problem to one or two components. So, ang troubleshooting is the application of logical thinking combined with a thorough knowledge of circuit or system operation to identify and correct a malfunction. A systematic approach to troubleshooting consists of 3 steps. First is ang analysis, planning, and measurement. So, analysis is the first step in troubleshooting. A defective circuit or system is to analyze the problem, which includes identifying the symptom and eliminating as many causes as possible. Next is planning. In this phase, you must consider how you will attack the problem. And lastly, sa measurement, you should be able to know the possible causes for you to be ready to make measurements such as voltage and resistance readings. Here are the selected K terms in Chapter 2.